Nice to meet you, everyone. I'm Han Junhee. In this video, we'll implement a feature to manage large numbers of enemy AI using Unreal Engine 5's Mass Entity. Create the project by adding the combat template in blueprint form. Once the project is created, first enable the Mass Gameplay plugin. After enabling the plugin, a restart is required, but there's no need to do that right now, so let's move on. Next, let's create a new open world level. Create a dedicated folder and save the level there. Next, we'll create an environment query asset for EQS. Click the asset to open it. In this graph, you can choose the basic shape of the spawn points through nodes. I'll choose a donut shape. In the Details panel, you can customize the spawn points for that node. If you drag the EQS asset in, it will be placed as an EQS testing pawn, and you can preview the spawn points in advance. Let's change the spawn points of the donut node. As you can see, the spawn points have changed, and you can preview them in advance. Next, we'll add a test so each point can be evaluated by score. You can access it by right-clicking, and we'll add distance. When you add distance, all points are filtered, as you can see. That is not the behavior we want, so let's change the distance test setting from filter and score to score only. Then all points will be evaluated properly. Since enemy AI should only spawn at reachable navigation locations, we add a pathfinding test. For some reason, the visual update isn't happening, but let's place the nav mesh first. Place the mesh at the origin and set the bound size to 1000 x 1000 x 1000. If you press P in the editor, you can preview the navigation area. You can see that the spawn points have been updated and unreachable paths have been filtered out. Now let's place a cone to add a slope to the terrain. Place it at the origin and set the scale to 100 x 100 x 5. Now move the EQS testing pawn to a suitable height. As you can see, spawn points on unreachable slopes become invalid. In this case, add a project test to bring the spawn point down to the ground. Of course, since pathfinding must be evaluated after the spawn point is brought down to the ground, move the project test upward. In this way, EQS can also be evaluated on slopes as desired. An EQS query can use any U object, but here we'll use an EQS testing pawn. So let's place a total of 4 EQS testing pawns in the level. Next, we'll create a character CPP class for the enemy AI. Once the editor has finished loading, we first need to add dependencies in build.ccs. Next, let's create a header file to group the structs and enums. Declare the UEnum class. This will be used to represent the enemy type. Let's make another enum. It represents the enemy spawn method. We'll either place enemies at random locations or spawn them according to a predefined EQS. Next, define a struct. This will be the value created by the spawn request. Next, create a developer settings class. Max spawn per tick is the value that limits how many enemies can spawn per tick. Next, we'll define the entity, config asset, and EQS asset properties to use for each enemy type. We'll define a property that determines which level the subsystem will be created in immediately. Lastly, define the grid space property to use when placing enemies by location. Then write the arguments in the uClass macro like this. Now that we've finished writing the developer settings, create a world subsystem class. Here we'll implement the overall mass spawning feature. Override should create subsystem, so the subsystem exists only in the desired level. Enemy spawning must only be performed where authority exists. Make sure the subsystem is not created on clients. Access it to retrieve the level asset set in the developer settings. Next, get the current world's map name as a string. Now iterate through the level asset array in developer settings and return true if there is a matching string. Next, we'll declare a total of 7 properties. This is the array that will hold the EQS testing pawns we placed in the world. Next, declare the EQS property. We also need the subsystem and navigation system used for mass spawning. The mass entity manager will be used to access mass entity fragments, meaning the values they own. Entity templates are the values that actually use the entity config defined in developer settings. Also, the hostile type array will be used when randomly spawning enemies. Next, we need to override on-world begin play. Developer settings are needed here as well. Next, we'll store all EQS testing pawns in the world in an array. Then we iterate through the entity configs in developer settings and register the valid ones. I'll initialize the remaining properties as well. I don't have header auto completion, so I'll add it manually. Now let's declare two additional properties for spawning. For spawn request, I used a queue for implementation convenience, but since we don't need thread safety here, I'll use a lock-free approach. This reduces unnecessary overhead. Next, declare a spawn timer handle to use instead of tick. Now declare the method that will receive requests. The reason for keeping the parameter as an R-value reference is to prevent struct copies. In particular, if the spawn location array has many elements, performance can drop significantly due to copying. When adding it to the queue, we also pass it as an R-value using moveTemp. Next, declare the method that processes requests added to the queue. Initialize the variable with the max spawn per tick value defined in developer settings. Next, we'll iterate through the requests in the spawn queue. In the case of dequeue, moveTemp is used internally to perform move semantics so no copy occurs. We validate the request. Here, that means either there's no need to spawn anymore, or no spawn location was provided. Next, we need to get the entity template that matches the request. We calculate how much to spawn this cycle. Now we spawn the mass entity. We also subtract the amount spawned from the requests remaining and remaining this tick. If any spawn amount remains in the request, add it back to the queue. If we've exhausted all remaining this tick in the current method call, we need to exit the method. Now, when a request is added, the timer will call the processing method. If all requests have been processed, stop the timer. Next, all spawned mass entities need to be moved to the correct location. Here, we'll use the navigation system to get the correct z-axis and use the entity manager to modify the transform fragment. First, use nav systems project to get a valid z-axis. This is the same project concept we used earlier in the EQS test. Second, access the transform fragment and update it with a valid location value. Now place this method immediately after entity spawn. First, get the actual spawn count. Now we'll use a loop to initialize the location that many times. But if we do only this, when the request is accessed again, it will reuse a spawn location that has already been used. We'll add an offset to solve this. I'll change this to actual spawn too. Now I'll create a method to get the EQS location. The callback parameter is a bit complicated. The red line is the format of the EQS query result value. The green line is an array that collects the result values from all EQS queries. If there are no EQS pawns collected in begin play, it won't run. Next, to run the query, we need env query manager. Now let's define a shared pointer to collect the query result values. The key is the number of remaining queries until the callback is executed. The value is an array that stores the query results. Now we need to iterate through the EQS pawn array and execute each query. The EQS pawn can be destroyed at runtime depending on the requirements. Check validity, and if there's a problem, decrement the key and skip it. Now we register the query delegate, and for safety, we'll register it with a weak lambda. Add the result value to the value. Decrement the key, and when it reaches 0, invoke the callback. Now just request the query through the query manager. Let's define a request method that can be called from outside. In the callback, we need to collect the locations contained in the query results. Check whether the result is valid. Next, we'll use the spawn location evenly for each EQS point. If we just divide by the number of EQS pawns here, decimal values could be lost. So for the last index, we calculate the placement count differently. Now we can just put the values into the location array as is. However, EQS query points are usually returned in descending order of score. So if we proceed like this, they'll only spawn at the same predictable location. To prevent that, I'll perform weighted random sampling so that it follows higher scores but still has randomness. I'll define a method to randomize the query result. I'll create an array to store random values. The float is the query point score, and the int is the index of the query location array. Next, I'll iterate through the array for the result items. For weighted random sampling, we need a valid score and U value. Here, the score will be the query point score, and the U value will be a random value. Now I'll calculate the weight with a logarithmic function and add it to the weighted array. Next, we need the actual count. Through the previous calculation, we created a weighted array where higher scores receive higher random scores. Now we need to sort it to access the higher scores. But in this situation, we'll only return as many locations as the count received as a parameter. So there's no need to sort everything. Here we'll use the quick select algorithm. Quick select is a derivative of quicksort, but unlike it, it sorts with O(n) time complexity instead of O(n) log n. In C++, you can use it like this. Weighted's getData is the begin iterator, that is the starting address of the array. Using the fact that adding 1 to an iterator gives the next address, we pass the parameters in order: the start address, the end address up to which to sort, and the position. The last one is the comparer used for sorting. Now it returns the location. Going back, we make the spawn point selected randomly. Then for each result, it will return a random location up to the batch count. Next, since we've gathered all the spawn locations, we'll use them to make a request. Now we'll add the request to the queue, and it's natural for the queue to own the request value. Move semantics are also used for this kind of concept. Next, we'll implement a function that places entities at the specified locations. We'll make a function that returns a location array in a grid format, but I'll leave out the detailed explanation here. We'll also make this function callable from the outside. The subsystem is more or less complete, and next we'll define the fragments. Here we'll define a total of 3 fragments. First, we'll create a fragment for the enemy to search its surroundings. It is better to register fragment properties with U property. That way, Unreal Reflection can detect them, and you can access the values through the mass debugger. Origin is the center of the radius that the entity will search. Define the search target point as well. Next is the time remaining until selecting a new target point. Now let's define the radius and movement speed. However, if these values do not need to differ for each entity, it is better not to define them in a fragment. Because a fragment is a value each entity has, if the number of entities grows huge, memory usage can be determined by the fragment. Through visualization, mass entity can spawn an actor when it is close and destroy it when it is far away. This approach is good for optimization as LOD, but it is not suitable for the method we will use. That is because the actor's state is not preserved. If you half kill an enemy and come back, and its HP is 100%, that is definitely wrong. So state data like this should be stored in a fragment that shares the same life cycle as the entity. Here, I'll simply manage health as a percentage. Next, let's define a fragment for death. The reason for separating it from the state fragment is that only dead entities will be split into a separate archetype and handled by a processor that performs dedicated logic. Briefly speaking, an archetype is a unit that groups entities with the same fragment combination. A processor is a class that queries fragments and tags across all entities and performs specific logic on matching entities. Now that we've created the fragment, let's initialize it in the subsystem. Next, let's define the processor. Let's override the method that sets the query conditions. I'll override one more method here and write the logic to execute in it. Next, add one property to use in the query. Set the flag that determines where the processor will run. Because this flag uses a bit mask, writing it like this makes it run everywhere except the client. Now we need to initialize the entity query like this. Here, we need to set the query conditions. For the entity to wander, it needs to modify its transform, so it should have a transform fragment. Also, since it needs to be modified, it must allow write access. It must also be an entity that has a wander fragment. But at the same time, it must not be in the dead state. It should not have a death fragment. Here, we won't read or modify any death fragment properties. Avoiding access when possible has no performance overhead. Next, if we set presence to none, it will search only for entities that do not have a death fragment. As I mentioned earlier, a processor can also query by tag. Here, when the entity is in the high LOD state close to the player, we want the actor to take control and the entity not to move. So we'll filter out that tag. We also want enemies to use only valid navigation paths. But if the entity is too far away, world partition unloads and navigation becomes invalid. For this reason, we'll also filter out very distant off LOD entities. Now let's write what to execute for entities that meet these conditions. For each entity chunk, iterates through the searched entities by archetype. It will invoke the callback once per archetype, but in the end, it still runs once for every entity, so there isn't much difference. Let's access the fragment data we need from the entity. Now we'll iterate through the chunk and access each entity's fragment. We'll calculate the time using the context delta time. Here, if the time is up, we'll find a new reachable location through the nav system. Next, we'll write the function that moves to the target location. Now we'll calculate the squared distance and the step size. We use the squared distance to avoid the square root operation. If the remaining distance is smaller than the step size, the entity doesn't need to move. Now we'll get the normal through inverse square root. This lets us get the direction without performing a square root operation. Of course, directly normalizing delta 2D would give the same result. Finally, calculate the next position and modify the transform fragment values. One thing I missed earlier, to modify a fragment, you have to access it by reference. Let's create one more mass processor. We'll define it the same way as before. The death processor must be able to read and write the death fragment. Next, as long as the entity is alive, its visualization will keep spawning an actor when it is close to the player. If you kill an enemy and an entity that should disappear after 10 seconds comes back, it might spawn a perfectly normal actor again. In the end, that would be a bug too, so here we'll solve the problem with a bit of a workaround. We'll restrict this fragment to read-only, since we only need to read it. As before, access the fragments used here. Because a read-only fragment cannot be modified, you have to access it as an array instead of mutable. I'll iterate through the fragment in the same way. The representation fragment indicates how the entity is currently being represented. Here, we check whether the entity is currently representing an actor. If an already dead entity no longer represents an actor, we'll request that the entity be destroyed. These kinds of requests can be made as deferred requests, allowing mass to execute them asynchronously at a safe time. Next, we'll make the entity destroy itself when the specified TTL expires. Let's initialize the entity query. Now let's set up the character to use with mass. The character needs a mass agent component. Using a mass agent lets us register delegates for when an entity represents or hides an actor. We'll create two methods for this. Let's register the callback. Often the activation callback can be called earlier than begin play. To prevent missing the callback, if we're already coupled with the entity in begin play, we'll call the callback directly. Next, let's define a method that syncs the state between the entity and the actor. In this video, we only handle the health percent, but if you're using gas, you could initialize the attribute set here or trigger animations or effects. To access the fragment here, write it like this. Now we'll access the status fragment through the entity manager. The target is the entity linked to the mass agent. Here you would overwrite the current HP, but since we're using the Blueprint combat template, this needs to be handled in Blueprint. For now, I'll skip ahead and implement the other side's sync first. Accessing the fragment is the same, so I'll copy it. Now I'll declare the getter and setter to be defined in Blueprint. Blueprint native events require an implementation by default in C++. Let's create it. The value doesn't matter, so we'll just put in a mockup. Now let's put the implemented method into the sync method. Next, I'll declare the actor integration callback to use in Blueprint. Now that all the required methods are done, let's finish implementing the entity callback. The callback triggered here is a broadcast from the entity subsystem, so it always fires for every character. So we need to filter whether the parameter is this character's mass agent. If it is, continue executing the callback. In this way, we've made it so the enemy character's state can be preserved through the fragment. Lastly, let's create a kill method so the enemy character can die. Here too, we need to access the entity manager. We want to add a death fragment to the entity when an enemy dies. But as I mentioned earlier, entities are grouped by archetype, and that's what makes ECS efficient. Because of this mechanism, changing an entity's fragment leads to an archetype change. Then the entity moves to a different archetype and causes a copy. In a case like death, which doesn't happen often, that's fine, but in general you need to be careful when changing fragments. I'll add the fragment using the deferred command approach. Next, we'll create a mass config. Write it like this. Now close the Unreal Editor and build the project. Once the build is complete, run the Unreal Editor again. First, for testing convenience, let's increase the combat character's movement speed and attack power. Increase the movement speed directly in the CMC. Next, we need to modify the attack power variable. Now we'll convert combat enemy into a mass-only character. Go into class settings and you can change the parent class. We'll change it here. Now let's finish implementing the getter and setter. The parent is mockup, so it's not needed. If HP is updated now, the HP bar has to update as well. Next, we'll receive the entity callback. The enemy AI controller should execute the state tree only when the enemy character is valid. We'll manage state tree activation through this callback. Find the state tree AI component in the AI controller. Of course, the AI controller needs to have a state tree AI component like this. After validating it, we'll run start logic. When it becomes disabled, run stop logic. Now, to prevent state tree from running automatically, uncheck start logic automatically. Lastly, let's change the combat enemy death logic to use the kill method we made. Let's replace the destroy actor here. Let's set the TTL to 5 seconds. Now we'll derive from this class to create a new enemy. As we decided at the beginning, we'll make it a zombie. For now, it doesn't need major changes. It just needs to look different. Let's create an entity config asset. First, we'll collect the traits common to all enemies, then derive from them later. The assorted fragments trait gives fragments to the entity. The mass actor fragment is needed for the entity to use an actor. The next two add the fragments we made. We didn't cover this earlier, but a mass trait can own fragments. Also, other traits may require specific fragments. The entity config we'll derive and use later will include the visualization trait, and that also has a transform fragment. So in that case, there's no need to add the transform fragment separately. However, even if a child config has a fragment, if it requires a fragment that the parent config doesn't have, an error will occur even if only the child is used. So to prevent errors, we'll add the transform fragment. Next, add the LOD collection trait. This trait collects the entity's overall LOD information. Add the simulation LOD. This trait will add tags like high LOD tag and off LOD tag to the entity. I'll set the distance and max count so it's easy to test. Make sure to enable set LOD tag. Next, add agent movement sync. This applies the enemy character's movement to the entity, so set it to actor to mass. Add agent orientation sync. This synchronizes rotation. For the same reason, set it to actor to mass. We've finished the common entity config, and now we'll create a soldier entity config as a derived type. Set the parent right away. Add the movable visualization trait. This trait creates an actor with mobility set to movable. With this, you can perform LOD across a high detail actor, low detail actor, and static mesh stage, but here we'll only use the high detail actor. Register the combat enemy we made earlier. Leave only high enabled and turn off everything else. This is LOD for actor representation. It's different from the simulation LOD trait that adds tags. Normally, it's cleaner to set it the same way as the simulation LOD trait. Visible LOD distance is the distance based on where the camera is looking. In short, base distance is distance culling, and visible distance is frustum culling. For max count, we'll only use high. Lastly, let's add debug visualization. I'll increase the culling distance so it's visible from far away. Copy the entity config we just made and create an entity config for zombies. You just need to change the actor class and the debug static mesh. Now it's time to register the asset in the developer settings we created under Project Settings. Register the entity config to match the element. Also register the EQS asset. Add the level that will use the subsystem we created. To run the test, set the level's game mode to combat game mode. We'll use the FPS command as well to check performance. Now let's go into the level blueprint. Here, let's spawn enemies through the subsystem. We'll spawn 300 soldiers. It looks like the player start is still below the slope. The nearby enemies spawn an actor and try to attack the player. But it seems like there's an issue because the debug mesh isn't following the actor. I'm not sure whether falling below the slope is because navigation is also being recognized on the lower terrain. First, let's check the spawn debug. It looks like the total number of entities doesn't reach 300. Let's create more EQS points. Now you can see that all 300 entities have spawned. We fixed the bug where the debug mesh, that is, the entity's position and the enemy character's position, didn't match. The issue happened because the entity config wasn't registered in the mass agent component. You can also register it as a common entity config, and in the case of the zombie character, it inherits this blueprint so you don't need to modify it separately. Now the entity's position and the actor's position are synchronized. Now let's create two entities and test whether HP is preserved. Let's also check in the mass debugger when the health percentage changes. The health percentage was updated the moment the actor was deactivated. If we activate the actor again, you can see that HP is preserved. After 5 seconds, the actor was destroyed. It wasn't updated in the mass debugger, and the entity has also been destroyed. The fact that the actor doesn't appear again proves this. Also, if you move away from a dead enemy, the entity is destroyed immediately. This prevents the terrible bug where dead enemies come back to life. Next, let's check whether the EQS points are really random. To check the spawn order, reduce max spawn per tick to 1. As you can see, it follows the score while still having randomness. The reason they spawn clockwise is that multiple EQS results are placed into the array sequentially. Another characteristic is that entities beyond a certain distance are not moving. This is because, considering world partition unloads, we set the Wander processor to be skipped for the off-LOD tag. Next, we'll run a performance test with a large number of entities. To do that, let's increase the number of EQS points further. We'll create 1,000 entities. Also, in the simulation LOD trait, we'll make sure the entity does not fall into off. Then all entities will execute the Wander processor. Even with all 1,000 entities executing the processor, it still maintains a high frame rate. You can also see some entities paused in the middle, waiting for the cooldown set by the processor. Lastly, let's test spawning using the location method. We'll use this pawn's location. You can see that they spawn properly in a grid pattern. And that's how we built a system to spawn and manage enemies using Mass Entity. The project we've worked on so far has been uploaded to GitHub, so please refer to it if you need it. Thank you for sticking with this long video, and thanks for watching.